Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we will discuss the braking of DC motors, and we will describe also one problem of starting of DC motor. So the objectives today will be discussing the stator as a starter of DC motor, what is meaning by starter of DC motor, discussing the shunt DC motor 4-quadrant operation, shunt or separately excited شباب, 4-quadrant operation, understand the different types of braking, regenerative braking, dynamic braking, and counter current braking. يعني hopefully to finalize all of these items today. يعني if we couldn't cover all of these items, يعني we will leave one item for the next class, inshallah. So the beginning, what is the meaning of DC motor starter? What is the problem of starting in DC machine? We described before that there is a problem in induction motor starter. Do you remember that?
Yes.
Yes. What was the problem? Yes. What was the problem? Yes, it was high. Yes. For how much the current in induction?
5 to 7.
5 to 7 times of rated current, exactly. So what is the problem now for DC motor? Do we have the same problem here? And let's discuss it and understand it. If the relation of armature current, you know armature current is equal to V term minus EA, which is the back EMF, divided by the armature resistance. At the beginning, you know, the speed of the motor is 0. At the 0 starting of the machine, there is no dynamics, so the speed is 0. So we expect that the EMF equal to Ka phi multiplied by omega, it will be 0 also. So yes, the armature resistance is normally a very small value, but in particular for high rating machines. So we expect a very high current at starting. So this is a problem in DC motor. And we will see in the examples, we will see how much current is starting in numbers to recognize the effect of starting current. So we have high starting current for DC motors. For how much it's high, we will see it in the solved problem chart. So what's the solution now? In the equation here, I starting equal to terminal voltage divided by the armature resistance. So simply we can add something here in the denominator to increase the denominator and decrease the whole number. So this is physically can be done by adding resistance. Or we can make another solution. We can decrease the numerator in order to decrease the whole number. So we can start with decrease the voltage. So we have two different methods. Either decreasing voltage or increasing resistance. This is numerically. How we can physically decrease the voltage?
Using chopper.
Using chopper, for example. So we can start with reduced voltage using chopper. Okay, so this is one solution. However, in conventional drives, the voltage control was very difficult. So they prefer to use the other solution, which is adding resistance to the armature circuit. So a well-known device called motor starter or DC motor starter, which is based on using added resistance to the armature winding in order to decrease the current at starting. However, in modern or advanced drives, we prefer the use of reduced voltage by means of DC chopper, because as we described before, in order to make starting and speed control and braking, we can use only one device. We prefer to use one power electronic device to perform all of these functions. So it's better to use voltage control instead of adding resistance. This is one side. The other side, if we add resistance to the rotor circuit, it means we'll have some extra losses in the beginning. This is not a big problem because the starting time is small, so we'll not lose a lot of power. However, we still prefer decreasing the voltage using one device, because we can use this device in speed control and braking as well. Okay, But to be honest, not all of the machines in industry now are using DC chopper. You may find some conventional devices in industry up till now. So we are going to describe starter, yani just in case if you find it in your work later, inshallah. So this is a device, shabab, which is called DC motor starter. Simply, as a beginning of the operation, the back EMF of the machine is 0 because the speed is 0. However, when we start the machine, we apply the voltage, the machine speed will start increasing. Is it right?
Yes.
And we expect the current, because the current equal to V terminal minus E divided by K phi. So, divided by RA. So we expect, because EMF is increased, the current will start decreasing. So
Yes.
this is the normal operation of the machine. So if we added rheostat or variable resistance to the motor in starting, we expect to limit the starting current. However, we need to speed up the machine operation. If you add high resistance to the machine, you will limit the current too much, and it will make the machine speed up slow. So we need to calculate it based on actual numbers in order to speed up the machine starting, and also to operate the machine or start the machine in safe way. So what is the principle or idea of operating this device? Simply, we have steps of resistances. So here, for example, we have 4 connected series resistances between 5 terminals from 1 to 5. And this device is based on working on the current which is going to pass here in this electromagnet, which will attract this handle and move the handle between points 1, 2, 3 up till moving to point number 5. And at point number 5, the motor will be connected directly to the supply voltage V terminal. So this is the method. However, we need to understand the analysis of calculating this resistance. So this is the aim of this part in the class. We need to understand what is the values for each steps, how many we need in order to start this motor. We will describe this operation based on a numerical example. So here we have, for instance, a motor of 10 kilowatts, 100 voltage, 1000 RPM DC machine, has armature resistance of 0.1 ohm and is connected to 100 volt DC supply. What is required? First, determine the starting current if no starting resistance is added. So we will connect the motor directly to the 100 volt and see what is the expected starting current. And also, it's required to calculate the current in values, it means in ampere, and in per units. Per unit, all of time we refer to per unit as the actual value divided by the rated or base value. So we need to calculate the current at the 0 time at starting. Simply, at starting, the machine speed is 0. So we can consider the EMF at starting equals 0, and simply we can substitute in the equations. So at starting, we can say IA start equal to V terminal divided by RA. So V terminal is equal to 100 volt and RA equal 0.1 ohm. So the starting current will be 1000 amps. Right. What is the value of the rated current of the machine? Simply, we can calculate this value from the rated data. We know from the nameplate data here, the power is 10 kilowatts and the voltage is 100. So by dividing power by the armature voltage, we can calculate the rated current. So rated current is 100 amps. So based on the value of starting current now, we have a current of 10 per unit, which means the current at starting is 10 times of the armature rated current or full load current. So this is high value compared to induction motor even. For induction, it was 5 to 7 times. Here, it's 10 times. And this value will stay for a part of time depending on the machine size. So if the machine is a high power machine, which means the inertia of the machine is high, so it will take some time to start up, maybe hundreds of milliseconds, or maybe around 0.9 or 1 second. However, if the machine is very small power or very small size, small inertia, it means the machine can start in several milliseconds. So based on that, the value of current will be. So for example, here, because the resistance is 0.1 ohm, the value of current is very high. However, if we have a resistance of 5 ohms, for example, so we expect at the starting we will have lower current, is right?
Yes. Yes. Yes.
So it depends on the armature resistance, and you know the armature resistance is basically depend on the machine rating. If the machine rating is very high, so it's expected to have high current. The conductor or cross section of the wiring of the winding of the machine will be high cross section area, and at that time the resistance will be small. However, for rating machines, we expect small current and small cross section, so the resistance will be high. So we can expect low starting current for low power machines and very high starting current for high power machines. Okay.
Okay.
So this is for that part. Number B, find the value of starting resistance if the starting current is limited to twice of the rated current. Recently we described most of the protection devices are working for overload condition between high full load to twice or 3 times of the full load currents. Okay, شباب? So twice of the full load current, it's still safe operation in a condition that we have to speed up the operation at this high current. So we can operate the machine at twice of its rated current, but for a limited time, not for the full time of the machine operation. So it's stated here, what is the value of added resistance required to limit the current to twice of the rated value? So simply, we have the rated value, which is 100 amps. So now we need to calculate the resistance added in order to keep the current within 200 amps. So simply, we can substitute in the relation and add the resistance to rheostat value in the denominator here. So we can substitute, the current is 200, the voltage is 100, and this is the armature resistance, and this is the required rheostat resistance. So simply we can get the value of the rheostat in ohms. So we need 0.4 ohms in addition to the 0.1 ohm in order to limit the current to twice of the rated current. Are we going to apply the 0.4 ohm resistance for all of time during starting, or we can make the operation in steps? Actually, as we described in the starter, we prefer to do it in steps in order to speed up the machine starting time. So how we can do that? This is what we are going to describe now in part number C. It's required here, this DC machine is to be run as a motor using starter box. Determine the value of resistances required in the starter box such that the armature current IA is considered within 100 to 200%. So we will limit the current to 2 per unit, and we need the values of the starter device. The meaning of a starter, as we described, Shabab, we move the handle between many points and change the value of resistance. So for now, we can imagine that if we consider this is the current with time, at the starting, we will limit the current, or we will allow the current to be twice of the rated current, as we can apply this at t equal t1. طيب, when we start adding resistance, we will add the overall value of resistance, which is 0.4 ohm. However, after a certain time, when the current reaches to 100 amp, we need to reduce the resistance in order to speed up the machine. For example, here in this problem, as you can see, for a current moving from 200 amps to 100 amps time, the speed is increased from 0 to 50% of the rated speed. Can you imagine if we leave this motor starting at the direct supply without any adding resistance? The machine will start very fast, however, the current will be very high. So we need to operate the machine safely, but at the same time, we need to speed up the starting operation. So it's preferred to start removing a part of the resistance, but in the condition to keeping the current lower than or equal to twice of the rated current. So at instant T2, we can remove a part of the resistance in order to limit the current to 200 ampere. And the current will start decreasing again, and the machine will speed up again until a certain value. At T3, we can reduce the resistance again, the condition of keeping the current maximum at 200 amps, and start repeating this step until reaching to the steady state operation. So this is the ideal starter. Now we need to calculate it in values. What are the steps and the resistance values at each step? This is the required in this part. So simply, we have, for example, we can have 3 or 5, whatever, we don't know now, but we will understand from numbers how many steps we are going to use. But if we assume, if we have 3 values of resistance, which means we have 3 startup values, so we need RA1 in the beginning, and then we will reduce the value of resistance to be RAE2, and increase it again to be RAE3. And at the last instant, at terminal 4, we will remove all of the resistance, which is the 0.4 ohm. So how we calculate this, Shabab? Simply, we can calculate based on the equations of the DC machine, but by calculating 2 times at each point, which means, for instance, at T2, we have 2 values of current. Can you see? We have a T2 current equal 100 amp, and at the same time, we have 200 amp. Is it right? From the figure?
Yes.
This is right. However, we can differentiate between them by saying, for example, T2 minus, so T2 minus, the current will be less than the 200 amps, which is 100 amp here, and
Yes.
call this point at T2 plus. So this is like the transient operation. We can consider at any instant that there is a previous value and there is value after this instant. So this is what we are going to do in order to calculate the starting resistance. So simply at T2, let's see the conditions. So for the first time, RE or RU stat 1 equal to 0.4 ohm. And in this case, we can calculate the current. As you can see, V terminal equal to EA plus IA, RA plus R rheostat, okay? And we can give the value of the armature current. So at T equal T2 minus, which means the current is 100 amp, we can substitute now in the relation and give yeah, is there a question? Is there any question, Shabab? Okay. So we can calculate at point number 2 at T2 minus. So we can say EA2 equal to V terminal, which is constant. It doesn't affect by the number of points. as the certain current, which is IA at 100 amps, multiplied by RA plus RE1. So this is the value of EMF now, شباب. It's 100 minus 100 amp IA at T2 minus plus, multiplied by RA plus RU stat. So this is the value of armature voltage EMF, which is 50 volt. Type. The question now, at the same time at T2, if A2 will change or not? شباب.
Will change.
At the same time at T2. At the same time, it means the speed is constant. It's right. Because the machine speed cannot vary within one instant. It will be constant value. So we expect at T2, the speed will be constant and the armature voltage or the back EMF will be constant as well. So we can, at T2 plus, the armature voltage will be the same. So we can say at T2 plus the current is 200 amps and the armature voltage,
the resistance is
but with the other value of resistance, RE2.
Yes.
Is it clear, Shabab?
Yes.
So we can calculate by this equation the value of R rheostat in terminal instant T2. Okay, any question?
Victor.
Yes?
We said the current will be the same. Why it's 200?
No, current not the same. Again, let's return to this figure. At T2, we have two values of current.
Okay, yes.
M at T2 minus and current of 200 amps at T2 plus.
Yes.
So we now calculated based on T2 minus, where the current was 100 amp, we calculate the EMF.
Yes.
The EMF will be the same at T2, whatever, minus or plus, because the speed is the same.
It's constant, yes.
Yes, so we can assume at T2 plus, the current which is 200 amps, the EMF will be the same and calculate the second step rheostat.
Yes, okay.
Okay, so the second step, Shabab, will be 0.15. So this means for the second step, we need added resistance of 0.15. So instead of 0.4, we need 0.15. This is at T2. Similarly, we can make the same for T3. At T3 minus, we will calculate E and use it at T3 plus by the same way and get the value of resistance. So we can calculate rheostat at point number 3 or T3. The rheostat value is 0.025 ohms. Simply, we can repeat this at T4. So at T4 minus, the current will be 100 amps and the same EMF which we have calculated, we calculate the EMF at 0.4 and substitute at T4 plus and get the value of rheostat. However, we could find that at T4 plus, the value of rheostat is negative. What's the meaning of that? The meaning is that we don't need this step, because if we remove the rheostat completely at step number 3, the current will not reach to 200 amps. You got it, Shabab?
Yes.
So this is the idea now. So based on our steps, when we start finding the resistance, the added resistance in negative sign, so we can say this step is not actual, and we can stop at the step bus, which is step number 3. So simply, we can say if we applied point number 4, the current will not reach to the 200. Can you see? The current is 125 ohms only. Sorry, 125 ampere. So we don't need this step. We can operate the machine only using 3 steps or 3 resistance or 4 steps. Our number of steps is higher than the number of steps by 1. Tamam? So now the values which we have calculated, we calculated the first time the 0.4, which is the total resistance. And in the first step, we could find the rheostat is 0.15. So we need the rheostat of 0.15. It means the value of R1 will be 0.25. So return back again to the first slide. So the value of the overall resistance is 0.4. Okay, Shabab?
Okay.
We need the value of rheostat at step number 2 equal to 0.25. So R1 will equal to all of the resistance 0.4 minus 0.25. Okay? So simply we can do the same for other steps. Resistance number 2 equal to the resistance of rheostat 1, which is 0.15 ohm, minus that A 3. So the value of resistance R2 will be 0.125. And the last value resistance will be 0.025. So it means we need 3 resistances. These resistances are 0.25, 0.125, and 0.025. As you can see, if you make the sum of these 3 values, it will be 0.4 ohms. So this is the way to make starting or a smooth starting for DC motor using starting a device. Any questions, Shabab?
How to calculate the speed?
How to calculate speed? Simply, you can go at each step and using the value of K5, and you now know the EMF. So, for example, let's go at step number 2, at T2. Calculated the value of EMF, which was 50 volt. Simply, the K5 from any loading condition. So at full load, and if we go to the nameplate data of the machine, here, it's written here 1000 RPM at rated. So we have speed, we can calculate K5, we can calculate E at rated, we have the rated current, we have the terminal voltage, we can calculate E or back EMF, and simply calculate K5 based on the rated speed. And then we can calculate speed at each instant based on the value of calculated EMF. Okay. So now we understood the starting problem of DC motor. So up till now in the DC machine, we described the speed control of DC machine. We described the starting problem of DC machine, and we are going now to describe the braking of DC machine. These are the 3 dynamics we need for controlling any kind of motor. Fine. For DC motor or for any kind of motor, we have torque speed characteristic. As you can see here in the right-hand side, this is the relation of voltage or speed with current or torque, but this is specifically for DC motor. However, if we consider any kind of motor, we just can refer to omega and torque. In the first quadrant here, the torque and the speed is positive. We call this quadrant as motor operation. If we reverse the torque, the machine will work in a mode called regenerative braking, or working at steady state, it will work as generator. Also, in the third quadrant, which means torque and speed will be reversed, this means the machine will be completely work as a motor in the reverse direction. So we call this mode as reverse motoring. And the fourth quadrant, the torque is positive and the speed is negative. So this is considered as regenerative or generator for the third quadrant. So we have 4 quadrants: motor, and its generator mode or regenerative mode, and we have reverse motor and its own regenerative mode. So these are the 4 quadrants of the of any electrical machine. For DC machine specifically, we have a relation between
Yes.
there is a message here to turn off what I don't know. Sorry? Just a moment, شباب. Okay, sorry. Okay, we can continue. So for the 4 quadrant control, شباب, we have a circuit in order to apply the motor operation at any mode. So simply, we can apply the operation in the 4 quadrants using this circuit, which is called 4 quadrant DC chopper. This circuit is called 4 quadrant DC chopper. The aim of this circuit is to reverse the current and voltage polarity on the terminals of the DC motor. So simply, if we are going to work in the motor at mode 1 for forward mode, we need to apply this sequence of switching in order to operate the machine as a DC motor in forward motoring. Let's discuss it in switching here, شباب. For instance, in first quadrant mode, if we apply switching, which is described here, as you can see, supply is connected through S1 and S4. So as you can see, S1 and S4, if we connect it or turn it on S1 and S4, it means the current will flow in this direction. Sorry, شباب. Again, the current will flow through S1 and S4 and return to the supply. Is it right?
Yes.
Right. Are we going to operate the motor in motoring mode for a full connected voltage for all of time? Which means if we have a supply voltage V equal to 600 volt, are we going to connect the machine to 600 volt for all of time? If we need to make speed control, we cannot apply the motor voltage for all of time. Is it right?
Yes.
So we need to control the voltage, for example. We need to reduce this volt. So what we can do is to control the voltage magnitude. How we can control the volt? Simply by turning on and off the switches. If we disconnect switch S1, if we disconnect switch S1, what will happen, شباب? يعني
The voltage will.
For the first case, when the current has flowed in this direction, there is a stored energy now in the machine.
Mm.
If you disconnect switch S1 and you have stored energy, what will happen? The stored energy will be dissipated. Is it right?
Yes.
So you have current flowing in this direction, so the current will go flowing in the same direction and force D2 to turn on, or D2 to conduct. Again, يا شباب. Now, for the first mode of the motoring operation, S1 and S4 are on, which means the supply is connected to the machine. And for time here, the current is charging. After a while, I need to disconnect the supply in order to control the voltage. So how we can do that? Simply by turn off S1. If we turn off the switch S1, and there is stored energy here in the machine, and S4 is on, the stored energy will force diode D2 to conduct, and it will make a short circuit on the machine in order to dissipate the stored energy on the machine winding resistance. Is it clear?
Yes.
Okay, so this is the first mode of operation. So we can summarize this operation here for the forward motoring. We have supply connection. If S1 and S4 are on it means controlled. I have to apply pulses for switches S1 and S4, and the energy can be dissipated through the resistance as the move when S4 is on, and D2 will conduct automatically. شباب? So
Yes.
the first mode of operation. Now assume we are going to make regenerative braking. For example, we are moving with a car to uphill, and are going to transfer to downhill. So when you are going downhill, you don't need to supply the machine. You need just to dissipate the energy. Is it right? So how we can raise the machine as regenerative braking or at generator mode? Simply, when you disconnect all of switches by making 0 signals for all of switches, this will allow the stored energy of the supply to force diode D1 and diode D4 to be on. Okay, شباب? So diodes D1 and diodes will be turned on. Why? In order to return this energy to the supply. شباب?
But you have to start it with the S1 and S4 is connected, right?
Just a moment. لا, S1 and S2 خلاص, S1 and S2 have been turned off.
Yeah, but from the beginning, you have to start with them.
I started the operation as motor.
Right.
Now I would like to start as regenerative.
Disconnect the 2 switches.
Just apply 0 signal for all switches. This will allow the current stored here to reverse its direction in order to work in regenerative mode and return the energy to supply. Like, what is the only way to return the energy to supply? As you can see, if the current is moving in that direction, it can force only D1, because if the current is moving in that direction, it cannot force D2, because the current is moving in from anode to cathode. So in that case, the current flow will be like that. The stored energy here will move the current through D1 and return to supply and come through D4. So this is the way of returning current to supply.
Yes.
If we need to control this regenerative braking, what we can do is to turn on switch S4. Turning on switch S4 will allow to move the current in the same direction D1,
Yes.
D4, S4 and D2. لا, this is wrong يا شباب. This part is wrong. I will modify it. Okay. And in order to keep the current in the same direction, so the current is moving in that direction now, we can turn S3 with D1. Okay. So this one should be S3 and this is D1. Okay. تمام كده يا شباب؟
Okay.
Again, in the supply connected mode, in order to return the energy to supply, the current will flow in that direction through D1 and D4. So in order to in order to make short circuit on the machine with the same current direction, so
Yes, of course.
need to apply D1 with S3 because the current in S3 moving in that direction. Okay, شباب? So this is the right values for this move. This is for regenerative braking or generator mode. طب simply we can make the same for the other two quadrants. For the third quadrant, which is reverse motoring mode. As you can see, for reverse motor, we need to make the current and the voltage polarity negative. So this is the positive current direction, and the positive polarity of volt, this is positive and this is negative. So we need to reverse, which means current is moving in that direction, and the polarity of voltage to be positive here and the negative there. So this means we have to turn on S3 with S2. So to supply the motor at reverse mode, we need to connect S2 and S3. Type in order to control the voltage again, we have to make chopping this voltage, which means we have to short the machine for a part of time. So how we can short the machine for a part of time here? In that mode, we need to turn on S2 and D4. Again, let's see it in the figure here. The current now is moving in that direction. So in order to make short circuit, we need to turn S2 with D4 to flow the current in that loop. Is it clear, شباب?
Yes.
So this is the reverse motoring mode. The last mode is the at reverse operation, or we call it reverse regenerative or reverse generator mode. We can simply do the same. You will find the supplies connected through D2 and D3 and the motor shorted at S4 and D2. تفضل زياد, you have question?
Yes, دكتور. بالنسبة للريفيرس دايركشن موتورنج, هل ال S3 خليها اوف ولا اون؟
يعني it's better to rephrase your question in English because it's to be يعني.
But for the switch 3, do we close it or do we make it on or off?
Switch 3?
Yes, at the reverse.
For reverse motoring, you are discussing this mode now.
Yes.
This mode. For this mode, we need to connect S2 and S3. Let's see it on the figure now. In order to connect the supply here, the positive to be here, we need to turn on S3. And in order to move the current in that direction and return it to supply, we need to turn on S2. Is it right?
Okay.
So S2 and S3 has to be turned on. This is for reverse motoring operation. And in order to control the voltage, we need to make short circuit on the machine for a part of time. So we can keep S2 on in the same direction because the current is moving here in that direction, and diode D4 will be forced to be on in order to complete or discharge the stored energy. Okay كده؟ Is it clear?
But Doctor, is S3 will be off or on at motor shorted?
It will be off.
Okay, do we have to switch off?
Yes, it will be turned off. So in this mode, S3 will be turned on if the supply is connected, and it will be turned off when the supply is disconnected. And we need to conduct short circuit on the motor. Is it clear?
Okay, clear.
Is the point of turning on and off شباب clear for you for the supply connection or motor shorted or not? يعني why we need to make supply connection and why you need to make short circuit of the motor? And this is a question for you. Is it clear for you or you need يعني more details?
Yes, clear, Doctor. But what will happen if we didn't we disconnected the supply, but we didn't conduct one of the S2 didn't conduct?
Your question, you said, what will happen if we turn off all switches?
No, if we disconnected the supply and we didn't make them short.
First, we need to agree together the connection or disconnection will be only through the power electronic elements. We are not physically to disconnect the supply from the circuit. Okay? This is
okay.
Number two, we control the operation and reverse motoring. Why we need to control? We need to control the applied voltage magnitude. So if we applied the gating signals to S2 and S3 for all of time, it means the applied voltage to the motor will be the value of V. This will not allow us to control the machine speed. But in order to control the machine speed, we need to make chopping, as we described in the last lecture. In terms of DC chopper, شباب, we described before in last class, if we have DC chopper like that, if we applied pulse during T on, and this is the full cycle. So this is a pulse. If we apply the pulse to the switches of S2 and S3 together, the voltage will be the applied voltage V, if this is V capital, and this is V A. Is it clear? If we apply the switch S2 and S3 on for all of time, you will not have this off time. You will have complete voltage, which means the average voltage applied to the machine is V. If the same to the input supply voltage. Is it clear?
Yes.
Right. In order to make speed control, we need to control the value of VA. How we can control it? By chopping this volt. How we can chop to make at this instant S2 on and S2 off here. Okay, so here S2, sorry, S3 off. So here S3 is off, and here S2 is on, and S3 as well is on. Okay, here S3 off and S2 on. Is clear, يا شباب?
Yes.
So in that case, we will have average voltage here. And this average voltage will represent the applied voltage to the machine, and we can control the machine speed. Okay, so it's not only a matter of applying the polarity of voltage and current and leave the amount of voltage. We have to control. So in order to control, we have to apply this mode, which is here in this part. For reverse motor, we have to turn off S3. If S3 is turned off, so the energy due to the current which is moving in that direction has to conduct any kind of diode with the available bus. So we have S2 is on. So if S2 is on, we need to find another way. What is the way now? Is it possible to move here? No place to move here because the diodes here will not conduct in this direction. Is it right? So we have only that direction. So it will force D4 to on in order to dissipate its energy. Okay? And in that way, we can control the machine voltage. So this is the way of speed control. Okay, كده شباب? Is it clear?
Yes.
Okay. Right. Last, for the reverse regenerative, we can apply the same by the same method. We can apply these sequences in order to get the reverse regenerative method. So by using this circuit, we can control all of the 4 quadrants. Okay, so by applying this control to this circuit, we can control all 4 quadrants. But remember, there is a fault here, and I will modify it in the slides and I'll send it to you on Blackboard. Okay. Let's go in more details for each type of braking, starting with the regenerative braking. As you know, for regenerative braking, the example we have discussed before, if we have a car is moving uphill in this direction, so we consume energy in order to move the car in the uphill. And if we are going down, we don't need to consume energy. We can return this energy to supply again. So how we can apply this mode? Simply by the second quadrant operation of the machine, as we described using 4-quadrant DC chopper. So this is the mode of regenerative braking, and these are the relations on the machine characteristics. So if we are working in motoring mode at point number 1, we can apply the relations of motoring mode. You remember, this is the relation of speed for separately excited or shunt motor. So at that curve from point 1 up till point 2, we can apply this relation, and we can calculate the current also using the relation IA equal to V terminal minus EA divided by RA, which is equal to torque load divided by K5. However, at point number 2, which means we reach it to the no load speed, and the torque is 0, which means also current is 0. So the relations we can apply here at that point, omega 2, which is the speed at point 2, equal to V terminal divided by K5, and IA2 is 0, which is equal to VT minus EA2 divided by RA, which is also equal to torque load divided by K5. And by this, in this case, we'll find that V terminal equal to EA. So the back EMF here will be the same like the armature or the applied terminal voltage. Right. If we increase the machine speed to reach to that point, and this point can be only achieved if the torque load is bidirectional. We described it before. We have two different types of. We have unidirectional load torque and bidirectional load torque. Bidirectional load torque, like the case in the electric cars. The torque load itself can be reversed. So at point number 3, what will be the relations? As you can see, for point number 3, the torque is reversed. So if we apply the torque in negative sign, you will find this sign converted to positive. And simply IA3 equal the same relation, B terminal minus E divided by R, but because the E will be higher than B terminal, you will find this part in negative sign. So it will be minus value. So the current will be negative. So for regenerative braking, as expected, the current will be negative, the torque will be negative, and the EMF and speed will be positive. So as you remember, the machine acts as motor if omega is lower than omega naught, speed is less than the no-load speed, and can act as generator if the speed is higher than the no-load speed. So if we have a relation between EMF and the speed, the curve will be linear like that, and the points can be assumed like omega 1 is here at motor operation, and at no-load speed, which is omega 2 at point number 2, you will find at that instant E equal to V terminal. And if E increased over V terminal, this will mean we are moving to regenerative mode or generator mode. We can summarize the regenerative braking in this diagram or this table. So for the operating points 1, 2, and 3, first for point 2, which is motoring mode, the torque load is positive. The terminal voltage for all of time will be in positive sign. The armature sign for point 1 is positive. The speed is positive and less than the no-load speed. The field is positive all of time and we have no control on the field. The armature voltage is positive and it's lower than the terminal voltage of the machine. So this is the motor mode. If we go to the no-load speed, the machine will work as no-load, which means the torque electric will be 0 because at the top hill we have no current flow and the machine don't need any power to flow the machine. So at point number 2, torque load equals 0, armature current equals 0, omega equal no-load speed, and the armature voltage equal to the generated voltage, or EMF equal to the terminal voltage. At point number 3, which represents regenerative braking or generator, the torque load is reversed, the voltage is the same, armature current is reversed, speed is higher than no-load speed, and the generated voltage is higher than the terminal voltage. So this is a summary for regenerative braking. We can have example for regenerative braking here. We have DC shunt motor has a rated I mean, the screen is not appeared for me here. Rated armature current of 76 amperes, so I rated equal 76 at speed of 1000 RPM. The armature resistance of the motor is 0.377 ohm, and the field resistance is 110 ohm. Rotational losses are 1 kilowatt. The load of the motor is bidirectional, so it means when we go to regenerative, the machine can reverse its electric torque. Calculate the following. First, we need to calculate no-load speed of the motor. So no-load speed simply we can calculate based on the given data. So during operation, we need to calculate first the K phi for full load. So EA or armature voltage equal to V terminal minus IA RA. So V terminal 440 minus RA multiplied by the full load current. So this is the value of EA, and simply we can calculate K phi at the rated speed, E divided by omega, which is 2 pi multiplied by N divided 60, and N at full load is given. So we can calculate the machine constant. Now we can use the K phi constant in order to calculate the no load speed. Simply, no load speed is V terminal divided by K phi, which is 440 divided by 3.93, which is equal to 111.9 rad per second. So this is the no load speed at that point. The second part, what is the motor speed where the armature current is 60 amps during regenerative braking? Basically, during regenerative, it means we are working in that quadrant. So if the current is 60 amps, we need to calculate the machine speed. So simply at point 2, the machine speed equal to V terminal divided by K phi plus, because it's in regenerative braking, plus RA divided by K phi square multiplied by torque load, or we can use the relation based on the current. So V terminal minus RAIA divided by K phi, and we have to change this sign to positive because the current will be in negative sign. So 440 plus 0.377 multiplied by 60 divided by K phi will give the value of speed. We have to consider that the no load speed should be lower than this value because we are working now in generating mode. So if we compare to omega node, we will find that omega node was calculated here 111, and here we have the speed 117. So this speed is higher than the no load speed. The third part, find developed torque during regenerative braking. Simply we have the current and we have the value of K phi, so we can multiply K phi by I to calculate the developed torque. So developed torque equal to K phi multiplied by the current, and this will be the value of K phi. Next question, what will be the back EMF at the regenerative braking? Simply, we can calculate EMF as K phi omega, and we have omega, which is the speed at point number 3, and simply get the value. Basically, it has to be higher than the terminal voltage because we are working in generating the mode. So terminal voltage was 440, and here the generated voltage or back EMF is 462 volts. Next, we need to calculate the terminal power at point number 1, which is motoring mode. Simply at motoring mode, the power input to the machine equal to the terminal voltage multiplied by the input current. However, this machine is said to be shunt motor, and the field resistance is given. So the terminal current or input current is equal to the armature current plus the field current. So we need first to calculate the terminal current and multiply it by the terminal voltage to get the power. So simply I line or I terminal equal to armature current at point 1 plus IF. We calculated armature current at point 1 is given 76 amps, and we have the field resistance value, so we can calculate the total current, which is here 80 amps, and we can multiply I1 by terminal voltage to get the input power to the machine. So the input power at motoring mode is 35.2 kilowatts. Number 3, it's required to calculate the input current of the machine at, or not input, it will be output. Output current of the machine at point 3, or let's say terminal current. For the regenerative braking, the machine is working as generator, which means the armature current is reversed. So if we apply Kirchhoff current law to the DC machine, DC shunt machine, we will find that the armature current equal to field current plus line current. So simply line current is equal to armature current minus field current. So we have armature current of 60 amps at 0.3, it's given, and we can subtract the value of IF, so the terminal current or line current equal to 56 amps. Next, it's required to calculate the generated power by the generator. Simply, we can calculate the generated power by multiplied the gap, which is E multiplied by I, yani assuming the generated power. Yes, generated power, it means شباب the power at the supply or generated voltage, which is the gap power before the losses of the machine. So simply we can calculate E multiplied by I, which we call it developed power. So we can multiply E at 0.3 by the current at 0.3 and get the generated power. So this is a developed power. It's required also to calculate the power that the machine can deliver to the loads, or the machine or the generated power that's going to return to the supply. To calculate this power, we have some losses in the machine. It's stated in the machine that there is rotational losses of 1000 watts, and also we have resistances, so we have some copper losses. So in order to calculate the returned power to supply, we have first to subtract the all losses, which are I square R for any resistance in the circuit and the rotational loss of the machine. So simply the losses are R armature multiplied by I armature square plus the field losses, which will be V terminal squared divided by RF, plus the rotational losses, which is given of 1000 watts. So we can calculate the losses here, which is 4.12 kilowatts. Then the power that's going to return to the supply will be the generated power we have calculated here minus the lost power. So this power will be 23.64. So if we
we can calculate it in another way, right?
Actually, we can calculate using many ways. What is the way you need to calculate?
VT times IA3.
It will be the same. No problem.
I3.
Yes.
Yes.
Yes. Most of relations, and you have some approximations for sure in our relations, but it should give close number, not a with very large error. Okay. Now we need to compare between the return power supply and the input power to the motor during motoring operation. As you can see, for motoring operation, we consume 35.2 kilowatts. And at regenerative braking, we return 23.64, which is almost around 2/3 of the power. Is it right, Shabab? So instead of applied mechanical brake for conventional cars, in electrical cars, we can use electric brake and return this energy to supply. Definitely, this means electric car efficiency is much higher than conventional cars. Is it right, Shabab?
Yes.
Okay. Any question in this example? Okay. So this is what the time is done. So we can stop at this point in this lecture, okay, and we can continue in the next lecture, inshallah. Now we can discuss your questions.